It's my great pleasure today to introduce as our first external SysRead speaker of this semester, Vijay Chidambaram of the University of Texas at Austin and VMware Research, who will talk to us about new directions in storage systems. So I'll hand over right to Vijay. Enjoy.
Thank you, Malti, for the introduction. Hi, folks. So I'm Vijay Chidambaram from UT Austin and VMware Research. And this is a talk that was a keynote at APSys recently. So it's very broad, like it may be a little different from the talks that you used to, which usually I think go deep. So feel free to stop and ask me questions at any point of time, and we can like talk more about any specific line of work, right? As it is, it's pretty broad, but like we can go deep wherever required. Okay. All right, so I mean, this is my usual sort of like pitch as to like why storage systems are important. Anything that you do today, right, whether it's cloud services or mobile applications, key value stores, databases, they all have storage as their bedrock, right? And any data is sort of the fundamental thing we all manipulate in all of these applications, and storing the data safely and handling it correctly is sort of like the job of the storage system. So recently, storage system designers have like lots of new challenges, right? So there's new hardware. For example, there's a new thing called persistent memory, which recently came out in 2018, and I'll talk more about that later. We have DNA storage on the horizon. Folks at Washington and Microsoft Research are working on this. There's Project Silica from Microsoft Research and the folks at UK. And these are all different forms of storage technologies that will become commercially viable in over the next 5 to 10 years, right? So these are all things that are coming. And they all have very different properties than the storage that we have today. We have new applications. So we have machine learning, which has changed the patterns that storage systems see quite a lot. We have blockchains, which put new pressures on storage systems. We have regulations such as GDPR, which sort of like changes what data you have to store, how you have to process it, and so on. So this is all new challenges. And we also have like new metrics to sort of like care about, right? So since SSDs have come along, the storage devices that we have limited lifetimes. So if you think back to like, like tape and hard drives, those are very long lifetimes. Like in fact, you can still take tape that was recorded like 60, 70 years ago and it would still work, right? But SSDs of today and persistent memory that's coming out, that's all have a limited lifetime. So you can only write to it a certain number of times before the device says, I'm done, I can't write to this sector anymore. I don't have any other sectors to remap. So this device is now like, like purely read-only. So device lifetime becomes an important thing that we have to sort of like care about in designing storage systems. So in this talk, I'm going to talk pretty broadly about how my group has tried to tackle all of these challenges. So we have a couple of like persistent memory work that I will talk about. We built a file system, and we have an approach for converting data structures from DRAM to persistent memory. We have built storage systems for machine learning, for training deep neural networks, for public blockchains, and we've looked at how GDPR affects storage systems. So I'll talk a little bit about all of these things. I'll also talk about the write optimized key value store that we built called PebblesDB, which increases the device lifetime and the throughput by reducing the amount of stuff you write to storage. And this has sort of like positive effects on both lifetime and throughput, right? So all of the work in this talk has been done by my students at UT. So all of the credit goes to them. And as we sort of like go through the talk, I'll sort of like point out who did like which work, right? So first, I'm going to talk about new storage technologies, persistent memory, sort of like in particular. So Intel announced this new technology in 2018 called persistent memory. So this is technology that sits alongside DRAM on the memory bus. So you can think of it as DRAM, but it has certain differences. So while it is accessed similar to DRAM, its read latency is a little bit higher. So for reading like a single word or a cache line from persistent memory, it takes about 2 to 4 times longer than DRAM. Read bandwidth is significantly more limited, and write bandwidth is also more limited than DRAM. But the thing to remember is that persistent memory is durable. So if you write something to it, even if you lose power, that is still retained. So the sort of like way to think about persistent memory is it's like really, really fast storage, because it's about like, an order to 2 orders of magnitude faster than SSDs to the previous fastest storage technology that we could use, right? So it's not as fast as DRAM, slightly slower, but much faster than the storage devices that we have today. And it's accessed in a different way compared to the storage devices we have today. So there's been a lot of research on how do you build storage systems for persistent memory, because persistent memory has been promised for a really long time. People have been working on this for like a really, really long time. So there's people have worked on data structures for persistent memory, and the goal here is to have high concurrency. So multiple threads, multiple cores accessing the same data structure, and it should be consistent. And if we lose power because it's durable, we want to ensure that the data structure is in a sane state, that you can do reads and writes after you recover from the power failure. And there's been lots of work in this line, right, across the years. People have also built file systems for persistent memory, right? So now again, the goal is, because it is very low latency, you want to ensure that you don't squander the low latency by having a very fat software stack, right? So the goal is for the file system to be very efficient, to have high concurrency. And there's again been lots of very good work in these lines. But if we take a look at the file systems that are available today, right? So let's see what the state of the art is. So here we have a graph where the different persistent memory file systems are on the x-axis along with the device itself. Y-axis is the time taken in nanoseconds. And what we're doing is we are appending a single 4 kilobyte block to a file. So in storage systems, it's a very, very common operation. When you have databases, when you have indexes, logs, whatever, usually append to the end of a file. In this case, what we're seeing is that to write 4 kilobytes to persistent memory, it takes 700 nanoseconds. So this is the leftmost bar in the graph. To do the same thing, to do the file system operation in ext4, and DAX means direct access, so it's a special mode for persistent memory, it takes 9,000 nanoseconds, right? So there's a 12x difference between writing 4 kilobytes to the device and appending 4 kilobytes to a file. And this is a huge overhead, right? I mean, like it's 12x, and you expect some overhead because, like, a file system operation is more involved than writing 4 kilobytes to a device, but it shouldn't be like 12x, right? So this is basically squandering all the nice latency that you can get from the device. If you look at the other file systems that we have today, PMFS, Nova, and Stata, they do better. They do better than ext4, which is the mainline persistent memory file system in the Linux kernel, but they still have high overhead. Like Stata, which is the previous state of the art, still has about 2.5x overhead. It takes about 2,500 nanoseconds to do an append operation, right? So they have high software overhead. So how do we reduce the software overhead of file system operations for persistent memory? So that's the main question we tackle. And the idea is a very old and well explored idea, right? So they're going to handle data operations in user space, right? So for data operations, we don't want to get into the kernel at all. And we want to handle metadata operations via an existing file system. Specifically, we want to handle that via ext4. So this is sort of the new part of SplitFS, which is that we are not going to create a new sort of slim kernel layer or anything. We're going to reuse what is already there. ext4 is like a very mature, robust, well-developed file system. So we're going to use that to do the metadata operations, right? We're not going to use any research file system. We're going to use just the mainline production file system for this. Right? So building on this idea, we have this file system called SplitFS, done by my students. This was in collaboration with Georgia Tech, Sanindya and Kesu at Georgia Tech, and Ashish Kohli at Penn State. So SplitFS is a POSIX file system for persistent memory. And the central idea again is to handle the data operations from user space and to handle the metadata operations via an existing persistent memory file system, right? And why did we do this? And the reason is that data operations are simple. So if you want to handle them in user space, you can, but it's possible to do a good job and to do it correctly. but metadata operations are very complex. If you look at POSIX, for example, it has lots of corner cases related to metadata operations. So re-implementing all of that in user space is a very hard task, right? And we're bound to make mistakes. So the question is, can we just reuse ext4, since they have put in like decades of work into making sure to get all the POSIX corner cases correct, right? And the bet we are making is, by using ext4, which is not it's not super optimized for persistent memory, we are making a bet. We are saying that most workloads have enough data operations such that if we speed those up, we can pay a cost on metadata operations. And we are not going to do anything special for metadata operations. We're just going to use ext4, but that cost will be worth paying because all the complexity of metadata operations is handled for us by ext4. So that's the high level bet that we're making with SplitFS. So if we compare how this sort of like compares to prior work in the space, right? So there's been like sort of like two extremes. So on one extreme, we have ext4, PMFS, and Nova, where everything is done in the kernel. So if you do data operations or metadata operations, you will do a system call, and that's going to go via the kernel, right? So that's one end of it. And this is low performance because persistent memory is so fast that if you're going to do a system call for every operation, that itself is like, it causes a lot of recovery, right? On the other end, we have file systems which are completely in user space. So everything is in user space, like startup, for example, right? And the problem with this approach is that it's a high complexity. You are re-implementing the virtual file system, VFS layer in user space, right? So there's high complexity associated with this. There's been sort of like intermediate points, like for example, ARI from Wisconsin in Eurosys, where they have data operations in user space and metadata operations in user space, but for certain coarse-grained operations, such as like allocations, they go into the kernel. So they get like an extent allocated, and then they're free to use that, do metadata operations on it in user space. So ARI's sort of like main goal was to support different kind of interfaces, like not POSIX, right? So that sort of like main take was that for each application, we want to provide a different sort of interface, not POSIX. So the goal was not really the same thing as us. And it sort of like shows in their low performance. For example, they are 30% slower than ext4, whereas we want to be much faster than ext4. So in the middle comes SplitFS, where the data operations are in user space and the metadata operations are in the kernel. And we get low complexity because we're not doing anything for metadata operations, we're just routing it through ext4. It's going to handle all of it. But we get high performance because like all the data operations are not going through the kernel. And we are betting that most workloads have enough data operations such that overall performance is going to be increased. So this is the high level architecture of SplitFS. We have two components. So we have a user space component, uSplit, and we have a kernel component called ksplit, which is just ext4 tags. So when you're doing reads and writes, the kernel component is not part of it, and it just goes from the application to the uSplit library down to persistent memory. The kernel is not involved. We are not doing system calls in this part. When we're doing creates, deletes, renames, all the metadata operations, we are going to go to ksplit, to the kernel component. ext4 is going to handle it just as if the application was directly using system calls to do these things. So we get all of the complex metadata operations taken care of first. uSplit also keeps a log to provide strong properties such as atomic data operations and so on. So we use a log, user space log, to do that. So to sort of like summarize, right? SplitFS accelerates your common case data operations by leveraging the work that's gone into ext4 tags and its maturity for metadata operations. That's how we get sort of like the best of both worlds. And we feel this is a very good architecture for building persistent memory file systems. We shouldn't be sort of reinventing the wheel every time. It uses logging and out of place updates for providing strong guarantees such as atomic and synchronous operations. All right, so if we look at the performance, right? So we go back to our previous chart where we were looking at the time taken to append 4 kilobytes. And we see that we have SplitFS, right? And it takes about 1250 nanoseconds to do a file append. Now SplitFS has different modes. So strict is the strongest guarantees that SplitFS can provide, where all operations are atomic and synchronous. So if you do a 4 kilobyte append, when it returns to you, that 4 kilobyte is durable and it's synchronous. So it's immediately done. So even in that strict mode, right, the overhead of SplitFS is about 80% compared to the device, right? So it's less than the cost of writing an extra 4 kilobyte block, which we think is like pretty good for, given that a file, an append operation is actually pretty complex, right? I'm not going to go into the details of like all the performance experiments that we did, but we have compared against, for example, we have used workloads such as LevelDB running the YCSB workloads, SQLite running TPCC, and so on. And what we show is that across all of the data-oriented workloads, we do much better than Nova, which is the current state of the art, while providing the same guarantees. For workloads such as Git, tar, and rsync, which are sort of like metadata heavy, we have about a 15% overhead because like that's not really the use case that we're targeting. It's fully metadata. So in that we have a 15% overhead, and we feel overall this is a good trade-off to make, because for database and key value store applications, you get like massive speedups like 2x. While for like Git and tar, you have a small, modest performance degradation, right? Okay, so SplitFS is open source. So general policy in my lab is that we make everything that we do open source. We have put in some effort to make it, well documented and like, usable by other folks. So definitely check it out. And if you want to use SplitFS in one of your research projects, we'd be more than happy to help you get it set up and so on. Okay, so I'm going to move on sort of like the next piece of work. Any questions so far about SplitFS?
Hi, Vijay. This is Rodrigo. Yeah, I have a question. Can you go back to the slide where you have the overheads? I think the previous one.
Yes. Oh, the other one? Yeah.
Yeah, this one.
Yeah.
So I'm slightly confused because essentially you're redoing everything that like you're using ext4 code to do the metadata operations, right? And the data you do directly.
Yes.
But 4 kilobytes seems awfully small for the difference between ext4 DAX and SplitFS. Like, can you elaborate this a little bit more?
I see. So for appends, we are not actually going down to ext4 DAX. So appends are still handled in user space by SplitFS. So when you do an append, what is effectively happening is we have what we call a staging file in which we put your 4 kilobytes, and we have a small entry to a log that we write. So that's all that happens in the critical path in SplitFS. And that's why it is much faster than ext4 DAX. We are not actually using ext4 DAX for this.
I see. Okay, so you're not actually going through the code path through the kernel.
No. So if we replace this operation here with, for example, create, we would have the same performance, actually slightly worse performance than ext4 DAX. But for data operations, and we count append as a data operation, we are much faster.
Okay, that makes a lot of sense.
Mm-hmm.
The other question is, once you go back to the user, if you have to do some metadata operation and you do that through the kernel and you get back a handle or something where the library can operate, how do you guarantee that the user space is doing the right thing, and how do you guarantee security in that case?
So whenever we are opening a file, that still goes through ext4 DAX, which does do all the permissions checking that you would do normally. So we don't, so SplitFS allows the same set of files to be accessed as you would normally if you're using ext4 DAX. So when you create a file, that goes through ext4 DAX, does all the usual permission checking and so on. So it's only once the open or the create has been successfully performed by ext4 DAX that we cache that handle, and we use that to do further operations. So we don't allow any operations that ext4 DAX would reject.
So essentially, the kernel is still giving you all the capabilities or the handles to the user space, and the user space can't do anything with the wrong capabilities, right?
Correct. Yes.
All right. Thanks a lot.
So just a very quick follow-up on Rodrigo's question. When you said the 4 kilobytes get written to a log, can you comment on how the durability guarantees of splitfs differ from ext4 DACs, if at all? Because if that log is in memory and not flushed to a disk, right, then if you had a crash, you would lose the 4 kilobytes, right, which is different semantics from ext4 DACs.
Right. So here in this experiment, we're using splitfs strict, which means that when the 4 kilobyte operation is done, it is synchronous and it's durable. So it's immediately on persistent memory. We don't write it to DRAM in between. So it goes directly to persistent memory. We do have other modes like POSIX, where when you do a write, it is actually in DRAM, and only when you do like an fsync, for example, is it returned to persistent memory. So in that mode, if you crash, you could lose data, but not in this particular experiment.
So the log is in persistent memory.
The log is in persistent memory.
Okay, that answers my question. Thank you.
Okay, so let me move on to the second part, or one of many parts of this talk. So the second question we tackle is, how do you build concurrent data structures for persistent memory, right? Because remember that persistent memory can be accessed very similar to DRAM. So you can build like, hash tables and linked lists and all of this stuff in persistent memory, similar to how we would build it in DRAM, right? So how do you build these data structures? And we have 3 goals. So the first is concurrent. So we want to allow multiple threads and multiple cores to access this data structure. We don't want like, big giant locks holding everything up. We want it to be crash consistent. So if we crash, we are still able to access the data structure. It's in a same form. We want it to be cache efficient, right? Because persistent memory is read and written in the unit of cache blocks. So when you read something into your like, L1, L2, and L3 caches, a full cache line is brought from persistent memory into your volatile caches. So cache efficiency is an important metric that sort of like drives how performance efficient your persistent memory system is. So you want it to be cache efficient. Now, unfortunately, when you have concurrency and you have crash consistency together, they lead to bugs because each is pretty hard to tackle. Together, they're kind of like a nightmare. So we looked at existing state of the art, like there's a fast and fair B tree and the CCEH hash table designed for persistent memory, and we found bugs in both. They were like subtle bugs that had to do with like concurrency and crash consistency, but they would lead to data loss and corruption, right? So pretty serious consequences. It's very hard to get these things right. So the question is, can we convert existing DRAM data structures to persistent memory data structures? There's already been decades of research and development into DRAM data structures. Lots of people have worked on this. And so like, can we take advantage of this somehow and not write data structures from scratch for persistent memory? And the sort of like insight that we had, which is, other people have had this before us, is that in certain DRAM data structures, you have isolation. So if you have multiple threads and they're doing writes at the same time, you have mechanisms in the data structures to prevent one thread from interfering with another thread, right? If you have another read concurrently going on with the write doesn't interfere with the read. So you have mechanisms to ensure isolation. And we find that this is very similar to crash recovery, right? In crash recovery, what you want to ensure is that if there is a crash, after the crash, your reads read consistent data. If your writes look at some partially written data, they're able to fix it or ignore it. So the same guarantees we have in isolation between different concurrent threads is similar to the guarantees we want between a write that happens at the time of a crash and a read or a write that happens after the crash. So it turns out that you can use the mechanisms for isolation for crash recovery in persistent memory data structures. So we built this work called Recipe based on this. Again, a collaboration with Georgia Tech, Sekwan and Jayashree were my students who worked on this. It's a principled approach to convert DRAM data structures to persistent memory data structures. And you can't convert all of these data structures in this way. There's specific data structures that you can convert in this manner, but we'll tell you how to do that. So we converted 5 different DRAM data structures and indexes, like for example, mastery, from their DRAM version to their persistent memory version, right? And these included hash tables, B trees, static trees, so different data structures, right? And in all cases, we had to modify only like 200 lines of code, right? This was about, tens of thousands of lines of code for these data structures. So it was like quite low in comparison to the full data structure. And the really interesting thing was, in comparison to handcrafted, designed from scratch persistent memory data structures, we got up to 5 times better performance. And this is because we took data structures that are really good, right? That have been around for a really long time, that are cache efficient, highly concurrent, and we made sure that they're crash consistent, right? And when we did this, we found out that like not only were they correct, they were actually like they had really good performance, because we are standing on the shoulders of giants in this case, right? Okay, so how do we do this? So isolation ensures that despite concurrent writes, right? So multiple threads are reading or writing at the same time, a read should return the correct value. So regardless of another thread writing, if you read a particular key in a key value store, it should return the correct value, right? In crash consistency, despite an arbitrary number of crashes, a read returns the correct value, right? So that's the guarantee that we want. So if we wrote x equals 10, regardless of how many crashes happen after that, when we read x, we want 10, right? So this connection has been noticed by other people before. Like for example, folks from Michigan had memory persistency paper in ISCA 14, which basically said the same thing. And our sort of like, we build on top of this and we say we can reuse the isolation mechanisms in DRAM data structures for crash recovery, because they're so similar. And let me show you how, right? If you take lock-free data structures, they don't hold locks in read paths. So a reading thread may encounter a partially done write. Okay, so the readers can tolerate this inconsistency. So a very simple way to think about this is, imagine there's a sorted list and another thread is inserting some item. So a partial state you may see is, duplicate values. So for example, you may see 1, 2, 3, 3, 5, right? And the reader can basically skip over the second 3 and think, oh, it's just a duplicate, so I'm just going to ignore it, right? So the reader can tolerate the inconsistent state of the data structure. Writer threads can fix inconsistencies. So imagine that the thread which was doing, she was trying to insert and left the data structure in 1, 2, 3, 3, 5, suppose it crashed. Another thread which comes back can first ascertain whether the previous thread is still alive or not. And if it's gone, it can finish the job. It can either sort of like roll it front to 1, 2, 3, 4, 5, or it can remove the second duplicate 3, right? In the theory literature, this is called the helping mechanism, right? So this is exactly what we want for crash recovery, right? So we want the ability that if there is a crash, reads can tolerate inconsistent data and writes can fix inconsistent data. So if there are data structures which already do this, we have to do very little work to make sure they're crash consistent. So that's the main idea behind the paper. So let me give you an example, right? So in the paper, we have what we call conditions. So not all DRAM data structures can be converted to persistent memory data structures using this approach. So we have specific conditions that must be met. And if a condition is met, then we will give you a specific recipe to convert the data structure to a persistent memory data structure. So one of the conditions is that there's non-blocking readers and writers. Nobody holds locks, and writers fix inconsistencies. Okay, so what does this mean? So when a writer is doing an update, it's a sequence of ordered deterministic steps. So if they insert 10, there is like one location in the data structure where the 10 goes, and you do steps 1, 2, and 3 to insert 10. Okay, there's a specific commit step after which it becomes visible to other readers. So if the thread, if the reader is concurrently reading the data structure while the writer is doing this, it can tolerate the partial state that the writer leaves behind, right? You can see step 1 and 2 and then skip whatever step 3 and 4 was and then just continue. If another writer sees this, it first tries to determine, is writer 1 alive? And if writer 1 is dead, then writer 2 can finish this. It can, using step 1 and 2, it can do step 3 and then commit. So it can finish the operation, right? So this is the helping mechanism that we talked about. So now if we take this data structure and we crash after step 1 and step 2, these two steps are now durable in persistent memory. Another thread that comes along can finish this operation. It can look at step 1 and 2 and it can say, I have to do step 3 and commit on persistent memory, right? So it turns out that what we really need to do to convert this data structure from, DRAM to persistent memory is add flushes and fences, right? Because DRAM, you don't have to worry about flushing because everything is volatile, right? But in persistent memory, remember that the data is kept in your volatile caches, has to be flushed from the volatile caches to durable persistent memory. So we have to ensure that we do flushes and fences because these are ordered operations, right? So step 1 has to complete before step 2. Otherwise, the thread can't reason about what is going on. So step 1, flush, fence, step 2, flush, fence, and so on. Once we do this, we inherit the correctness of the DRAM data structure. If the DRAM data structure was correct and concurrent, our converted persistent memory data structure is correct, concurrent, and crash consistent, right? Because we're not modifying any of the core logic of the data structure. All we're doing is we're ensuring that stuff is properly flushed in order from caches to the persistent memory. So that's basically what we did. This is the secret as to why we had to modify so few lines of code to convert DRAM data structures to persistent memory data structures. Now, a big caveat there is, though the number of lines of code are small, it's knowing what lines of code to change that is the real challenge. So it did require some work on behalf of our grad student. So I'm not going to say this is a trivial thing to do, but assuming you understand the original DRAM data structure, then it is, you can use that understanding to convert it to a persistent data structure without sort of like undue changes in the code, right? There's still be the mental effort to figure out how the data structure works, but you won't have to write like 2,000 lines of code to do the conversion. So again, recipe is open source. We have like 5 different data structures. Again, like we highly encourage you sort of like use this in your research. If you're doing something in persistent memory and just want to use a highly concurrent data structure, just plug in something which you've done, and we'd be very happy to sort of help you set it up, right? So before I move on, other questions about recipe? Okay, all right. Let me.
I have a quick question, if I may. So the one difference between the persistent memory setting and the DRAM setting is that because you can crash, a computation may not run to completion, right? So in particular, a writer might not run to completion. And as a developer of a concurrent DRAM data structure, I might have the expectation that even though readers can see inconsistent states and whatnot, the writer will always eventually finish, right? Because I don't try to be crash consistent. So I'm curious how you managed to address that. Maybe that's in the 200 lines of code that you needed to change, but it sounds like there needs to be some way of restarting a writer from a checkpoint, so to speak, right? Because you have your flush checkpoints, but there might not be logic to restart the writer in that data structure to begin with, right?
Right. So there's multiple conditions that we talk about in the paper, and sort of like one condition is basically where everything that the writer does is sort of like in private memory, and then there is a commit step where you change like a single 8-byte word to make the whole tree visible, right? So in this sense, like what the DRAM developer will be thinking is everything they've done until the commit step will just be lost, whereas in persistent memory, all the stuff that you do is simply going to be not visible to other threads, right? So you're still using a private memory, but unless you do the final commit step, it will not be visible to any other thread. Does that help?
It does, but it opens up a new question of how a reader would then actually see inconsistent state if all the writing is happening in private memory.
There are many different conditions that we handle. So one condition is where the readers don't see anything until the commit step. That's actually the easiest thing to handle. The second condition that we saw was where the readers and the writers don't hold any logs, and the writers just like modify the data structure. So you could actually see intermediate state. And then the readers can also see that and they will have to tolerate it. So if you have this situation where the readers are seeing intermediate state, writers will also see this intermediate state, and the data structure itself will have a helping mechanism to finish that write or to roll it back, even though it's in DRAM, right? And we are basically borrowing that same mechanism.
Okay, let's move on. I think you answered my question that in the sense that there has to be a helping mechanism, but what isn't that clear to me is why that helping mechanism would be there for just in-memory data structure. But let's take that at the end, or maybe
right, sure.
maybe offline.
Okay. All right. So to sort of summarize these two works, right? The sort of big theme is we want to reuse existing code, right? So in SplitFS, we are reusing the existing POSIX file system, ext4. In Recipe, we are reusing existing DRAM data structures, right? So the idea is that even though persistent memory is new, it's very similar to either it's similar to DRAM, in which case there's lots of research about that, or it's similar to storage, in which case there's lots of research about that. So there's many things that we can take from existing research, and we should sort of be reinventing the wheel. So we should try to see how we can sort of minimal modifications, reuse existing work in the persistent memory setting. Now, doing this is not trivial. Doing this carefully requires lots of thought and care to make sure that you're doing the transition correctly, both for performance and for correctness. And that's where the challenge lies. But I'm sort of excited about this sort of line of work where we're trying to reuse existing. Okay, so now I want to talk about new applications for storage and how they sort of affect storage. I might go a little fast in this, given that we have about 20 minutes left, right? So there's three main things I'm going to talk about. So first we have machine learning, right? So the first question is, does storage matter at all when we're training machine learning models? Isn't it all about the GPU? So that's the first question. And how best can we use DRAM when we are training machine learning models? In the realm of blockchains, again, the same question. We always start with this question from my lab, right? Does storage even matter when we are mining blocks in a public blockchain? And how can we best design a storage system to support public blockchains? And then how does GDPR affect storage? And what are the sort of design principles there? So I'll sort of go quickly through this. So the first work is a collaboration with Microsoft Research. So let's look at the training pipeline for machine learning, right? And this is, I think, specific for deep neural nets. There are aspects that are more general, but in this work, we mainly looked at deep neural nets. So your data is going to be, let's say, on an SSD. And then you have your CPU with lots of cores and DRAM. And you read the data from your SSD into your DRAM data cache. You decompress it because data is usually compressed when stored in storage. And the compression factor is quite high. It's about 7 to 10x, right? And then you apply random transformations. So for example, if you are doing image related machine learning, you take an image and you rotate it or you crop it, you add random elements to it and so on, right? So you apply random transformations. An important point here is that these transformations have to be done differently for each round of machine learning. You can't pre-compute this. The learning actually comes from the fact that you're able to take all this and you do all these random transformations, and it still sort of learns from the data, right? So you have to do this sort of in the critical part. Once the data has been, decompressed and you do all these random transformations, then you send it off to the GPUs, and then it's processed there. So let's imagine in our setup we have 8 V100 GPUs. So not quite top of the line, but very good GPUs. All right. All right. So let's look at the data movement in this picture. So your SSD can give you about 530 megabytes per second, right? That goes through your data cache, and then the data cache can then give you about 800 megabytes per second, given that data is cached in memory. So you have higher overall bandwidth than what your storage can provide. You decompress it, and the decompression can occur at 1300 megabytes per second, and then you apply your random transformations and you send it off to your GPUs. The problem is that the GPUs are the most expensive thing in this whole pipeline, and you want to keep your GPUs fully fed and utilized at all times. But your GPUs consume about 2,300 megabytes per second, right? So your pipeline is unable to feed your GPUs at the rate at which it expects data, right? And if you look at our current pipeline, what's the bottleneck? The bottleneck is the fact that when you apply random transformations, you can only create the data at 735 megabytes per second. So in this particular pipeline, it doesn't matter if you had infinitely fast storage, right? Because your bottleneck is your pre-processing. So you need more CPUs to do more random transformations at a faster rate so that you can feed it to the GPUs. There are other models that we looked at where the random transformations that are applied are really simple, so you can do it at a very high rate. But your the data is big, and to read it from storage is like that's the bottleneck. So in the machine learning pipeline, you can have different stalls. So we call them data stalls, right? And if the random transformations are the problem, we call them prep stalls, preparation stalls, right? And if the problem is that, like, like for example, the data from your storage is coming in too slow. For example, the data is stored on a hard drive, a fetch stall, right? Because you're not fetching data fast enough from storage into your main memory. And what this sort of line of work shows is that in order to keep your GPUs fully utilized, you will have to solve both prep stalls and fetch stalls, right? And there are different techniques that you can do to sort of solve this problem. Sometimes it's a hardware problem and you can't really do anything without throwing more hardware at it. But there are many cases where you can actually do clever things in software to significantly reduce data stalls. And we built a tool called the DS Analyzer, which answers what if questions, right? So for example, in the previous picture, we asked what if storage became faster? The DS Analyzer would basically say, nothing would change, your bottleneck is in prep stalls. What if the number of CPUs or GPUs is increased? If the number of CPUs increase, prep stalls may go away. If the number of GPUs increase, now we may suddenly have more prep stalls. So the DS Analyzer can answer all of these questions based on a training run through the entire pipeline. So I believe it will be quite valuable to developers. We also built Cordial. It's a new data loading library. If you know about like the DALI library from NVIDIA, it's similar to that. And what we've shown is that using Cordial, we can speed up machine learning training or DNN training by significant amounts in many use cases. For example, when you do hyperparameter searching, we can increase that by 5x. If you do multi-server training, we can increase the performance by 15x and so on. And all by reducing data stalls, right? So data stalls matter a lot for many different use cases, and we're able to find and resolve data stalls. Okay, so that's a high-level takeaway I want to give from this part of the work. So sort of like moving on, I'm sort of moving fast through the space. The next thing we looked at is like blockchains. Okay, so this is collaboration with VMware Research, and specifically we looked at public blockchains like Ethereum and Bitcoin and so on, right? And the idea there is that the blockchain will release a new block every n seconds. So for example, in Ethereum, it's like about every 10 to 15 seconds, a new block with transactions is released, right? The rate at which you release blocks is set so that when a block comes out, it can go through the rest of the network, propagate through the network, and other nodes can verify this block and start to build on it. So if I release a block and I know that the rest of my network will take 10 seconds to receive this block and process it and be ready to work on it, that's going to be the rate at which I release blocks. If I know my network is really fast and my computers are really fast and I can do it in 5 seconds, I can reduce n to 5 seconds. So what we are showing is that there is a direct correlation between the timing taken to process transactions in blockchains, in public blockchains, and overall throughput. Because you're basically waiting until everybody can receive blocks and process them. So this actually matters. This is actually highly correlated with how your storage system is built. Because when you're processing transactions, you are reading data to verify that the transaction is correct. And so we built a new storage system to support this, and we show that this can increase performance by about 20 times compared to Ethereum, essentially by reducing the time at which you can release a block, or by increasing the size of a block that can be released every n seconds. So unfortunately, I don't have like more time to talk about this, but I'd be happy to answer questions about more details about this. So again, going really fast. We looked at GDPR, which is the General Data Protection Regulation from Europe, went into effect in May 2018. And the question we tackled was, how does it affect systems and storage in particular, right? And this was a collaboration, a very fun collaboration with the UT Law School and Arun at San Diego, right? And this was led by my postdoc Supreet, who's now at University of Iowa. So I'm very happy for him. So we analyze GDPR from a systems perspective. And what we find is that every piece of data in GDPR now needs 7 pieces of metadata. So for example, if you collect some data from a user, who did I collect it from? And what purpose can I use it for? How long can I keep this data? Because different pieces of data can live for different amounts of time under GDPR. You can't keep data around forever. So what we saw was that this metadata explosion, right, that is happening really slows down systems, because now you have to keep a lot more metadata around. You have to answer queries based on that and so on, right? Long story short, we have this new benchmark called GDPR bench, where we have like we extended YCSB to have the queries that can be sent to like a processor or a storage node under GDPR, and we measure how your system sort of like actually reacts to these GDPR queries. And we measure sort of like Postgres and Redis, and we show that like Redis actually struggles a lot with GDPR because its architecture is it's not a good fit for what GDPR requires from storage systems. All right, final thing. I talked about new metrics earlier in the talk. One of these new metrics is how much data is written to storage devices, because they have limited lifetimes. A sort of related metric that comes along is IO amplification. So let's say imagine the user writes 10 gigs, but then the server, the storage system receives like 50 gigs. So the write amplification is then 5. If the storage system receives 500 gigs, the write amplification is 50, right? So why do we care about this, right? First, LevelDB, RocksDB, these systems have very high write amplification, around 20 to 50 times. And if you take an SSD that can last, let's say 5 years, assuming 5 terabytes a day, very decent, with like 65x amplification, which is what RocksDB has, it can only write about 75 gigs of user data, right? A far cry from 5 terabytes, right? It's like a fraction of what you paid for. So can we tackle IO amplification? So we built this key value store called write optimized key value store called PebblesDB. This is a collaboration with VMware Research. And the sort of like main high level idea that I want you to take away is that LevelDB and RocksDB, they have high write amplification because they rewrite data a lot to keep it sorted always. So whenever data comes in, they rewrite all the data to keep it sorted so that if you get a read, you can do binary search to find the data. So reads are quite fast. But the cost is that you have to keep rewriting your data to keep it sorted. In PebblesDB, sort of like key high level idea is that you can actually keep data partially sorted so that like, there's a balance between your read performance and your write performance. And you drastically reduce the amount of write traffic you're sending down to the storage device. So we see that PebblesDB gets about 3 to 6 times better write performance than RocksDB. It writes about half the amount of data and it gets similar read performance. The thing that is affected is range queries. So range queries are a little bit slower in PebblesDB because your data is not fully sorted, right? Okay, so that's a lot of stuff that I covered. PebblesDB, as before, is open source. Would love to help you guys use it in your research. I'm going to skip the future challenges section just so that we have some time for questions. But let me actually skip over to like the conclusion, right? So the main takeaway I want to give is that it's a very exciting time to be a storage researcher. So 20 years ago, right, there used to be like hard drives and nothing else, right? Or like SSDs were just coming out. So there's not a lot you could have done with storage at the time, right? So it was not super exciting to be a storage researcher. But right now, there's so many new challenges. There's new applications, there's new workloads, there's new hardware, new metrics. So it's a very exciting time to be a storage researcher. And if like any sort of like, like junior grad students are watching this at ground, like, like definitely get into storage research. It's a good time to do that, right? So sort of like another high level takeaway I want to impress is that we want to reuse existing systems and data structures as much as possible, right? There's now been like, like 25, 35 new data structures developed for persistent memory, and all with like subtle bugs, right? So this is very hard to do correctly. So whenever possible, we should reuse existing systems and data structures so that we inherit their correctness and the fact that they've been debugged over like several decades. And another thing is like in several of the work that you saw today, I collaborated with a lot of people, and especially like theory people, right? So PebblesDB came from collaboration with theory folks. For recipe, we borrowed a lot of stuff from theory. So interdisciplinary collaboration leads to better and stronger results than if you just did pure systems work. So I highly encourage people to sort of like collaborate with sort of like especially with theory folks. And with that, I'd be happy to take questions. Thank you.
Hey, Vijay. Quick question. I may have to leave, unfortunately, so I'm just going to jump in the front of the queue if you don't mind. You also did some fun stuff on trying to analyzing these programs for crashes and stuff like that, right? Did you want to comment a little bit about, I really enjoyed that work too, in addition to more core systemsy work. Just wondering what you've done with that and what you're finding.
Yeah, I mean, I couldn't fit it in with the talk, but we did this work called Crash Monkey. Which basically tries to determine if file systems are correct when they crash, right? It's sort of like an important property you would expect of file systems, right? And what we saw was that we built this infrastructure where we would emulate a crash. So the state of the art before that was basically you either pull the plug or like you would have a virtual machine and you would crash the virtual machine, both very slow and would take a lot of time. So the insight was that what really matters in a crash is what is the state on storage at the time of crash, right? Nothing else matters. So you can wipe everything in memory, very cheap operation. So you just have to emulate what is on storage at the time of the crash. So we built this tool called Crash Monkey, which does this. So if you give it a workload, it will emulate a crash at different points. And then it will mount the file system on top of this crash state and see if it recovers correctly. So we have an oracle that we compare to. And so we looked at previous crash consistency bugs that have been reported. And what we found out was that a lot of the bugs could be reproduced on a clean file system doing very few operations. I think this is partly due to the fact that more complex bugs don't even get reported because it's hard to trace it back to crash consistency. But of the bugs that we saw, all could be reproduced or most could be reproduced on a clean file system. So then we built Crash Monkey to explore that. So basically what it do is it would take a simple 100 megabyte small clean file system. It would systematically do different operations. It would crash. It would test whether there is a bug. And we actually found very interesting bugs. For example, in ButterFS, which is a Linux file system, rename was not atomic under certain conditions. And this was like very shocking because a lot of applications depend on rename as sort of like the central linchpin, right? So it turns out that that bug was like sitting in ButterFS for like 2 years before we found it. We found a whole range of other bugs where, for example, if you punch a hole in your file and then you crash, now that can leak sensitive data and so on. So we found about like 12 bugs across like different file systems, and the sort of like underlying thing in Crash Monkey is that it's very systematic. Like if you give it a search space, you tell it like this is what you have to search, it will create crash states, crash, do the whole thing. And it actually like it was very interesting, like kind of like DevOps, because my student at the time when we were doing this was running about 700 virtual machines across 70 different nodes in Chameleon Cloud while we were doing this, because like you had to do it in parallel, right? So we had to do this, and like it was a lot of fun to sort of like, he was basically DevOps manager for a while. But like we found a lot of bugs, and it was a very fun paper, and we contributed the test to the Linux kernel. So the Linux kernel now has tests that Crash Monkey found and bugs that Crash Monkey found and so on.
Thank you. That was a really useful summary for people who haven't read the paper. So that was great. And so you should still read the paper. It's a nice paper. I'm just wondering what you think is like the future in that line of work. Was that a one-off for you? Is that a thing you're continuing to do, or?
We are now trying to find bugs in persistent memory file systems. These are a little bit different because in Crash Monkey, what we did was we intercepted all the reads and writes by having a fake block device. So instead of like actually going to the device, we would intercept it using a fake block device. In persistent memory, you write directly to persistent memory. There's no intermediate software layer. So that makes it very difficult as to how we do this. So we are approaching actually two different lines. So I have a wonderful new student called Haley, and she's a
But you're writing through an API, right? That gives you your interpolation point, does it not?
Yes.
You're
so we
writing
directly,
bytes. It's not like a x equals 3. I mean, there's there is an intermediary.
Correct. So memcopy, for example, is an intermediate point at which we could intercept, and we are doing that. And we are also sort of like reusing a lot of the crashing infrastructure to sort of like do this. And we have found one bug in Nova. It's not an earth-shattering bug, but it's a bug that only will occur if you run with one CPU. So like, it sort of like adds rigor to the systems that we test, but we are exploring bugs in persistent memory file systems.
Oh, thank you.
Yeah, I mean, like, I know there was like a lot of information, like, sorry if it was like too much of an information dump, but happy to answer the questions.
I have a question, like a philosophical one. It is indeed a very exciting time for storage and so forth. And there's a convergence between memory, persistent memory, and storage. And I don't have a really well-formed question, but why do we need file systems anymore if we have persistent storage? And of course, one of the reasons is that files are a standard way of exchanging information, right? So like, where do you see this going? Like, is Apache Arrow trying to come up with a common in-memory representation that is not proprietary to a particular program in the right direction? How do you feel this whole space evolving in the next decade?
Yeah, I mean, it's a very good question. So in my opinion, files are not going to go away. And applications which use files are also not going to go away. So we are always going to have both these sort of like modes of working, where one mode is where, like you said, like we're just going to have data structures, and we have libraries like Intel's persistent memory development kit, which will basically memory map an entire device and then build data structures in that space, right? So there we're not going to have files. We're going to have, I mean, I guess we're going to have very coarse-grained files, but your interactions are not going to involve files in the theoretical part. So that's one part of it, right? The other part of it is like, we're going to have lots and lots of legacy applications which will require files which, which need fast access to it. And so both of these things are going to coexist. And one of the lines of research we're actually currently pursuing is, can we build a file system which is good for both of these things? So right now, a lot of file systems are optimized for the file use case and not a lot for the memory map use case, right? And so we are building a new file system where we look at the different designs possible for file system, right? And it turns out that if you do certain designs, that kills your memory map performance. But there are designs where you can have good file access performance and memory map performance. And the project is basically showing you how do you build such a file system, and like what is sort of like the challenges there.
Oh, so cool.
Okay, so we are almost out of time, and I want to make sure that we don't set a precedent here where in SysRead only faculty get to interrogate the speaker. So it'd be great, and I'm sorry, Rodrigo, for cutting you off, but it would be great to have a question also from a student before we wrap up.
Well, we can come back to Rodrigo's question after that.
And we can come back to Rodrigo afterwards, and we should. So now's your chance.
I'm happy to answer questions about other stuff as well. Like,
I actually had a question. So would you mind going back a couple of slides to the point where you were trying to build a what if analysis for?
Yeah. Let me see. So here or the next slide.
So would you mind elaborating a little bit on that? Like, how are you doing that what if analysis? Like, what's the technique that you're using essentially?
Yeah. So I don't know if there's a standard name for this. We call this differential analysis. So basically, doing this analysis is actually kind of tricky because you have a lot of asynchrony in the system and parallelism. So it's not like you can put timers to find out like how much time these things take, right? So what we're doing is we will do a run where we know that everything is cached in memory. So we have no hard drive or storage component to it, right? Everything is already available in memory. So we're just going to decompress, do the random transformations, and then feed it to the GPUs. So we'll measure the time taken for that and the bandwidth achieved for that. We will have another run where we already have random transformations done already. And we're just going to take that and we're going to feed it to the GPU. And we're going to see what is the rate at which the GPU can accept this data. So by doing diffs between one run where, for example, everything is cached versus another run where you have to read from storage, you find out what is the difference between these two settings. Does that help?
Yeah, it definitely helps. Perfect, thank you. I was actually kind of, because I'm a little familiar with like how the causal profiling works. So
Right.
I was wondering if it was something similar to that.
Yes, it is very similar to cause actually. Yes.
Okay.
Exactly. Mm-hmm.
Okay, so if there's no other questions, then I think we should go back to Rodrigo and make sure that he gets all his questions answered.
Yeah, my only other question is what, Vijay, what do you think of the Apache Arrow project?
I think
If
it's
it's going
still,
the right direction.
yeah, I think it's going in the right direction. So it's still pretty early days for it yet, but I do feel like just as with this sort of like uniform file abstraction, right? I do feel like we will need something similar in the memory mapped access space. I don't know if it's going to be Apache Arrow, but I do feel like the direction is right, and we definitely need something standardized there.
Okay, so then I will take the last question before we wrap up. And for if you have to leave next week at the same time, we have another SysRead talk by Arpan and Jonathan Mace from MPI Software Systems, where they will talk about machine learning training and running training and inference like clockwork on GPUs. So hope to see you again next week. But Vijay, just, I have this nagging question about the helping mechanism. I just want to make sure that I resolve that. So, if I'm writing a lockless in-memory data structure, right, then, I will not assume that my threads suddenly stop execution, right? So what I don't see, and perhaps help me understand, why would I put in a helping mechanism that allows me to sort of idempotently resume execution after a thread has just like blown up? Why would that be in the data structure to begin with?
So your threads can still fail. I mean, like, so the fault model is not exactly a crash, but they could fail for other reasons. For example, they could be out of memory. They could have hit a bug in something. So they're not trying to handle sort of like crashes like we are, but they are sort of like handling cases where a thread, when it is trying to do this operation, has stopped for some reason, right? Could be bug, could be resource exhaustion, whatever. And another thread which comes along is then trying to sort of like continue its work.
I see. And you found that those mechanisms were already present in the data structures report.
I mean, that's actually one of our conditions that have to hold before you can convert it to the system memory using this approach.
Okay, cool. Thank you. That clarifies it. All right. Let's thank Vijay again for coming virtually to give this talk. And I hope to see you again here next week. And we'll all you can follow up with Vijay. His email is on his website if you have any more questions. Hope to see all of you again soon. All right. Thanks, Vijay.
It was a pleasure.
Thank you.